Are we on? I think we're on. Hello, everyone. My name is Mason Doyle. I am actually your instructor for this abstract algebra course. I know I might be a little dark right now, but I am in what's called the light board room at Columbia College. So we have this awesome room where there is this plastic in front of me, this plastic screen, and I'm able to write on it and explain things. And what I wanted to do was I wanted to make some videos for this abstract algebra course. And I wanted, the purpose of these videos was so that I can make some content for you all that feels like I am lecturing you more a little bit, since you all don't have a traditional lecture style in this class. But also, I wanted to give you content that would help you for your upcoming quizzes. So you all may know you have quizzes in this course, and I'll be honest, they are significantly more difficult than maybe some of the homework questions that you are being asked, but they're also on a time limit, okay? So what I have done is I have looked forward to your quizzes that you all are going to have due. I'll stand more over here since I don't think my eyes are as shadowy on that side. But I've looked at the questions that are going to be on your quizzes in the future, specifically this one's for quiz 1. And I have constructed some example problems that, should you study them well, I believe you'll do great on your quiz 1. Okay? So this will be a sequence of videos that will allow you to study, get some more content, practice down. And yeah, I think it'll help you well. As always, please reach out to me if you have any questions. So one of the things that I wanted to discuss was this idea of a group, right? So a group satisfies 4 properties, okay? It's a set with a binary operation. That's not the property, that's just basic structure, but it satisfies 4 properties. It satisfies closure, associativity, inverses, and an identity element, okay? So, and there's a unique identity, and every element of the set has a unique inverse. So, with that said, one thing you'll be quizzed on is whether a given set is a group or not a group. And if it's not a group, is it a semigroup or is it a monoid? All right. So we are going to look at some examples of sets with binary operations, and we're going to see, is it a group or not? And if it's not a group, then what is it, if it is anything? All right. So let's get started with this. So this is the set of the positive or the non-negative integers with ordinary addition. So we must ask ourselves, is this a group or not a group? Well, feel free to pause to think about it. Well, this is not a group, okay? This is not a group. Why? So let me write that. Not a group. Why? Well, for one, not every element has a unique inverse, okay? So every element does not have a unique inverse. How can we show that? Well, what would be, so does an identity element for this exist? Yes, it does, right? So seeing that, what would be the identity element here? The identity for the non-negative integers under addition would be 0, because 0 acts as our do-nothing element, okay? So seeing that 0 in the set is the identity, okay, we have that for any x, that's a non-negative integer, what do we see? We see that x, well, I'm sorry, what we want to do is we want to construct a counterexample. So I apologize for that. So what we want to do is we want to construct a counterexample, okay? So let's think of a number. Let's think of a non-negative integer, and what's a non-negative integer? It's 2. So we can think of 2, 3, 4, a million, 10 million, any number that you want. as long as it's non-negative. So for 2 in this set, what would be the inverse of 2 in this set? Well, we want to add it to something that gives 0. But the only thing that gives 0 is -2. But the problem with -2 is that it's not an element of the non-negative integers, obviously, right? So we see that 2 plus x equals 0, which would imply that x is equal to -2, but that is not a non-negative integer, okay? Right? It is associative, right? So for any, let's just say, A, B, C in there, parentheses A plus B plus C equals A plus parentheses B plus C, close parentheses, right? We know that's true because addition itself is associative, okay? It also, it's closed. It's closed as any xy in the set. X plus y is also non-negative, right? So it satisfies closure as well, okay? So it is closed, it is associative, and it has an identity element, okay? So closed under its binary operation, identity, and associative, all that implies that this is a monoid, okay? So remember, a monoid is not a group because this doesn't have, every element doesn't have a unique inverse. However, a monoid is a weaker structure of a group that has associativity, it's closed under its binary operation, and it has an identity element, okay? And that's in your notes as well. Awesome. So that's why this is not a group, okay? So the non-negative integers under addition is not a group. So give me a second to erase this, and we will continue with more examples of sets. And I think I have 5 here. Feel free to skip ahead to when I'm not erasing this board, unless you need the break too. Okay, so the next one. The integers in the form of 3 times z with regular addition. So what this is this is the set of all elements plus or minus 0, even though that's just 0, right? Plus or minus 3, plus or minus 6, etc. Okay, with regular addition. Okay, so let me finish that off, right? Just say like etc. Right? Okay, so that is the set. So this is actually a group, okay? This is actually a group, and we're going to show it, okay? So we're going to prove that this is a group together, okay? So what you need to do is you need to show closure, you need to show associativity, you need to show there exists an identity element, and you need to show that every element has a unique inverse, okay? So let 3a, 3b, and 3c be elements of 3z, right? Where a, b, c, this is probably redundant, but we'll say it anyway, are all integers, okay? So elements in 3z look like this, okay? They look like this, 3 times the multiple of an integer, okay? So, what we want to do is we want to show closure, okay? So, consider 3a plus 3b, okay? What does this equal? Well, 3a plus 3b, well, that is 3 times a plus b. And what is this a plus b? We see a plus b is also an integer, okay? A plus b is also an integer, so it's closed. Okay, so it is closed under its binary operation. Okay, well, next we want to show associativity. Okay, so let me just say that for associativity, you should always kind of say like what you're trying to find. So for associativity, we see, what do we see? We see that parentheses 3a plus 3b plus 3c, well, a regular addition is associative, so we can move that across. 3a plus parentheses 3b plus 3c. These two things are equal to each other, right? Because regular addition is associative. So we say thus associative. Okay, that's my shorthand of associative. All right. So what would be the identity here? What would be the do nothing element in this case? Well, I have it listed here. The do nothing element would be 0. Okay. So remember, with identities, you want to show that it's two-sided, meaning that you can add it from the left-hand side or the right-hand side, and everything be good. Okay. So the identity would be, let me not spell 0, let me say 0. 0 in 3z as, and this is me showing this, 3a plus 0 is equal to 0 plus 3a, which is equal to 3a. Okay? So that's how we show that it is, that it has a identity element. Okay? So now all that remains to show is that every element has a unique inverse. Okay? So let's, for inverses, an element, we could say 3k in 3z, where of course k is an integer, has an additive inverse negative 3k, which is equal to 3 times negative k, right? Because negative k would be an element of the integers. Okay? So therefore, it works, right? Therefore, we have a additive inverse. All right, so one last fact about this one is also that it's called an abelian group. Remember, abelian is just a special name for commutative, okay? So if a group is commutative, we say it's abelian. It's named after a mathematician named Abel. He was such a good mathematician, we named commutativity after him in the context of groups, okay? So for here, I'll just say it is also abelian as for 3k1 and 3k2 in 3z, 3k1 plus 3 K2 equals, factor out the 3. Then we have K1 plus K2. Well, that just equals 3 times K2 plus K1, which is equal to 3K2 plus 3K1. And that's how you show that it is commutative, okay? And so, therefore, this is the proof. Let me get out of the way. This is the proof that this is a group, okay? So it shows all the properties of a group, okay? So your proof should look something along these lines, right? I would maybe add a few more words here and there, saying therefore, thus, all that stuff, right? But the biggest thing is you want to show all the properties, okay? And make sure that you're writing your proofs in complete sentences, all right? Because that is important. I think there's a spray bottle in here. No, I have this. See if this works. It might work a little too well. Oh yeah, too well. I said I had 5 examples. I may not get to all 5 just because I don't want this video to be too long. But once again, you can speed up me doing this if you want. Okay, so let's look at another set. More examples. We like these. We like examples in this class. So let's look at the set of, so this is the negative real numbers under multiplication. Think about this one for a second. Is this a group? Okay, first thing you want to check is it closed? Okay. So think about a negative real number times a negative real number. When you multiply them together, what do you get? You get a positive real number. Positive real numbers don't exist in here, okay? So this set is not even closed, all right? It fails at its most basic property, the closure property. So this doesn't even have closure. So it's not a group, because no closure. And what you need to do is you need to show a counterexample. Okay? So, so consider, so just pick 2 random elements. So pick -2 and -3. And those exist in the negative reals, right? And we see that -2 times -3 is equal to +6, which is not in the negative reals. Okay? So it's not even closed. Okay? So therefore, it does not pass the group test. Okay? And because it's not closed, it's not anything that we're studying in this class. Okay? This might be some type of structure that exists in very general, very, very general sets. Nothing we are studying in this class, okay? So, yeah, not a group. And not a monoid and not a semigroup either, because it doesn't have closure. Semigroups at least have closure. Remember, a semigroup is closed under a binary operation and has associativity. A monoid has associativity, closure, and an identity element. And a group has closure, identity element, associativity, and every element has unique inverse. Okay? All right, so more sets, more sets. So this is the positive rationals under multiplication. So the positive rationals Okay? All right, so is this closed? So this is a group, and we're going to prove it. Okay? So what would an element in the rationals look like? Well, they would look like fractions, right? So let A over B, C over D, and I put F over G. You don't want to put E. I didn't want to put E over F because E, excuse me, means an identity element in this class, right? So let those be elements of the positive rationals, okay? For closure, sorry, y'all. We have that A over B times C over D is equal to A times C over B times D, which is also a positive rational. Okay? Right? Because if A over B is a positive rational and C over D is a positive rational, then if you multiply them together, it'll give you a positive rational. Okay? So that's closure. Okay? All right. That's good. So for associativity, we see that if I have A over B times C over D times F over G, well, multiplication is associative. Normal multiplication is associative. So that is A over B times C over D times F over G. And that's good, right? We see that regular multiplication is associative, so this is not a problem for us, okay? So closure and associativity, we almost get for free, which is great, okay? What would be the identity? So for multiplication of positive rationals, so if I have a rational number, what can I multiply it by to get itself? You're probably thinking 1, and that's correct, okay? So here, the identity is 1, because that is a positive rational number, as, you got to show it, A times B times 1, A over B rather, times 1 is equal to 1, let me get that right, 1 times A over B, which is equal to A over B. Great, okay? We have shown it. Now, what would an inverse look like for an element? So every element does have a unique inverse. Have a, or an unique inverse. Let me say inverse. As y. For A over B in the positive rationals, what can I multiply by A over B to get 1? B over A. So, as we see, there exists a B over A in the positive rationals such that A over B times B over A is equal to 1. Okay? So that's good. And this is also an abelian group. It's abelian as A over B times C over D is equal to A times C over B times D, which is the same as C times A over D times B is equal to C over D times A over B for all A over B and C over D in the positive rationals. All right, and that is the proof that this is a group, okay? That's the proof. Now, one thing you're probably realizing is that this isn't hard, okay? I don't think that proving something as a group is necessarily difficult. It just takes a lot of steps. It takes 4 steps. First, show that it's closed. Second, show that it's associative. Third, show an identity element exists. And fourth, show that every element has a unique inverse, okay? Continue on in that pattern, and if one of those fails, then you don't have a group, okay? You may not see it's not a group initially, but you do want to keep trying, okay? So, there's that, okay? All right, let's do one more, and then I will cut this off, okay? An example, so you can fast forward as I erase if you want. Kind of gets caked on there, but it is what it is. Okay, this one's straightforward, so I don't need to erase the bottom one for this at all. So this one's a small one. That might hint to you that's not a group, but what is it then? All right, so we have R star under division. So the star here means that it's non-zero reals, okay? So 0 is not included in this. So, is this a group? Well, it's closed, right? So it's closed because if we have 2 non-zero reals and we divide them, we'll get a non-zero real, okay? So, closure, check, okay? Feel free to check it yourself, okay? What about associativity? This actually fails associativity, okay? How can we show that? Well, consider 2, 3, 4 in the reals. All right, so we can see what? 2 divided by 3 divided by 4, that does not equal 2 divided by 3 divided by 4. It just doesn't, right? Because that would imply that I had this reversed, I'm sorry. 3 divided by 2, it may work the other way, but this is how I had it. 3 over 2 divided by 4 does not equal 3 divided by 2 over 4. Yep. Also, there's no identity element, okay? There's also no identity as no E in R star such that E divided by X is equal to X divided by E equals X. That does not exist, okay? So let me erase this abelian side down here, that way you don't get that mixed up with anything else. And there you go, okay? So that's why. All right, so that was our first video, y'all. I hope you all enjoy it. I'm going to cut it off now and give y'all more examples in more videos. Thank you all.